Now, sometimes for second order ODE, we have something known as constant coefficients. So what it tells us is that the values for A, B, and C for this second order ODE, which is y prime prime, y prime, and y, are constant. In other words, they're just numbers. There's no algebra terms, no x terms, and nothing, yeah? And usually they always equal to some other term, which is either a polynomial, is a sine, cosine, etc. Now, what we're actually interested in this kind of video is the fact that the second order ODE has constant coefficients, yeah? So A, B, and C are just numbers. We can just pretend that we don't care about the right hand side, yeah? A little keynote, guys. When gx is 0, the function on the right, this entire equation is known as a homogeneous or linear second order ODE, yeah? That's just some key terminology. Now, we are only focused on the left hand side, as I was saying. Now, what's so special about constant coefficients? Well, it's actually super easy to resolve. The fact is that when you got A, B, and C, this entire equation becomes a quadratic equation. So you can think of the beginning part as am squared plus bm plus c must equal 0. And that's just standard quadratic. And when you solve it, you're going to have solutions for m. Now, these m could be one of three forms. If your solutions were real, in other words, you've got whole numbers for m, you can have a real root, so it will be y equals the first case, where m1 and m2 are different solutions. These will be your 2m solutions. However, you might have a case where your quadratic is repeated. In other words, when you solve it in the calculator, you're going to get two of the same answers. In that case, you take the second form. Now, be very careful, guys, yeah? The first and second form look pretty much identical, except the fact that you have an x over here, yeah? This makes it a big difference. And lastly, guys, you got the complex roots. Now, this only happens when you have a negative in the square root of your quadratic formula. In other words, you get an imaginary number. Now, notice here I got it's kind of like a longer version. You got e to the mr. Now, this mr means the real part of that root. So your root for complex solution usually takes this form, yeah. So if you solve your quadratic, you probably get something like, I don't know, let's say 2 plus minus 3i. Now, this part here would be your real part of your m. This part here will be your imaginary part. So that's what goes in here and here, okay? And then you just repeat it again for here and here. So now I'm going to show you guys 3 different examples which covers real, repeated, and complex roots. So let's check them out.
Okay, let's do this, okay? So, our characteristic equation based on this is going to be m squared plus m minus 2 equals 0. Okay, and now we just need to factorize this. So we need to find what multiplies to make 2. Because 2 is prime, it's probably going to be 2 and 1 for sure. 2 on your options we have. 1's minus, 1's plus. This is bigger, so plus 2 minus 1 is plus 1. So yep, this is it. Therefore, 2 values for m is going to be minus 2 and plus 1. Therefore, y x, let's call it yx, equals c1 e minus 2x plus c2e 1x. That's it. Easy, isn't it? Okay, so our characteristic equation would be m squared minus, so look at this one, 4m plus 4. So really just the coefficients in quadratic form. And then solving this quadratic equation, what do we get and how do we do it? I think we should have m, that's right, m minus 2, m minus 2. So actually we have repeated roots. Okay, repeated roots. In other words, we have m equals 2 twice. Alright, so what is the general solution for repeated roots? You know, actually for this case, it's not going to be the same as we've seen before. It's going to be a slightly different, tweaked up formula. There's a proof to it, but this is only the solution. The proof I'll post afterwards. Okay, so the general solution, I'm going to use just t this time. I've got board of x. So we have yt equals c1e to the power of 2t, the first one, plus, and this is where things change, c2, and now we have to add an extra variable, t here, e to t. So really it's the same thing, but this t is the thing that changes. Okay, the reason why I put this here, I suppose, is to kind of denote that you're not going to get the same thing, but there is a proof to this as well, which I can explain afterwards. We need to get m squared plus 2m, so just following this, plus 5 equals 0. Immediately we'll notice that we're not going to get real roots this time, so we'll actually get complex, or complex roots, which involves real plus imaginary. So the first thing we should do is use our quadratic formula. Let's calculate this here. So m equals, so let's memorize the formula. It's minus b, so a, b, c. A will be 1 here. Minus 2 plus minus b squared, which is 4 minus 4ac. 4 times 1 times c is 20. Over 2 times a, which is 2. And this should give us minus 1 plus minus, square root here is minus 16, which would be 16 root 16i. Root 16i over 2. Root 16 is 4. We're going to get 2i. So you guys can check this for me. So as you see, we've got complex roots. Now, unfortunately, we cannot do the same method as previous. So we're going to have another final solution. Okay, so a general solution, because we're using complex, we're going to have c1 e to the power of, first thing first, we got minus 1. This would actually be just minus x. So we just use this part. And then now, because this will be where the imaginary part will belong. And this is going to be cos bracket, the term involving 2i, so it'll be cos 2x plus c2 e to the power again minus x. And here, instead of having cos, we're going to have sine 2x. So this is all it really is.